We operate in a network environment where interception is an absolute certainty. Every packet of data you send travels through infrastructure controlled by third parties. To secure that data, we have to make the contents mathematically impenetrable. This is a bust of Julius Caesar. Roman armies relied on rudimentary substitution ciphers to protect military commands from falling into enemy hands. Today, the stakes operate on an industrial scale. Intelligence agencies continuously monitor global internet topology, vacuuming up network metadata and capturing massive streams of communication. Defeating this level of automated surveillance requires a mathematically rigorous approach. We use a system known as symmetric encryption. In a modern digital landscape, you cannot hide the fact that a message exists. Security relies entirely on rendering the intercepted contents useless to anyone who captures them. Every symmetric encryption scheme, regardless of its mathematical complexity, is built from exactly 5 foundational ingredients. This flowchart illustrates the basic model. We start with plain text, X, and a secret key, K. Both enter the encryption algorithm, which outputs ciphertext, Y, the scrambled result. To reverse the process, the decryption algorithm requires an exact duplicate key to translate ciphertext back to plain text. When evaluating the strength of this system, cryptoanalysts assume the adversary already possesses the complete algorithm and the captured ciphertext. The system achieves computational security only when the adversary is forced to guess every possible key to read the message. The entire strength of the cipher rests exclusively on the secrecy of the key. To see how the encryption algorithm actually scrambles the data, we have to look inside the engine itself. All encryption relies on 2 mathematical operations. Substitution maps existing bits to entirely new bits. Transposition rearranges the order of those bits. Look at this grid. Modern product systems take these 2 operations and layer them in multiple alternating stages. As bits swap positions and change states continuously, the algorithm destroys any statistical patterns that an attacker could analyze. There is an absolute mathematical constraint to these operations. No information can ever be permanently lost. The process must be perfectly reversible. Encryption does not randomly destroy data. It creates a state of highly structured mathematical chaos that can be cleanly untangled if you hold the right key. Many major block ciphers, including the data encryption standard, execute these operations using a specific architectural framework known as a Feistel network. This diagram shows the start of a Feistel network. An incoming block of bits is split perfectly in half, creating a left path, L0, and a right path, R0. The right half enters what is called a round function, labeled here as F. Inside this node, the data is mathematically combined with a subkey, K1, derived from the main secret key. The output of the round function is then merged back into the left half using a bitwise XOR operation. XOR, or exclusive OR, is a logic gate that outputs true only when its inputs differ, effectively scrambling the bits based on the subkey's influence. To complete a single round, the newly scrambled left half and the untouched right half cross over and swap positions. This establishes the inputs L1 and R1 for the next cycle. This exact cycle repeats. The algorithm typically loops through 16 identical rounds to ensure the data is thoroughly scrambled and computationally secure. The structural advantage of the Feistel network is its operational efficiency. To decrypt the data, you run the exact same algorithm, simply feeding the subkeys in reverse order. The internal engine is only half the architecture. We also have to define how data is fed into that engine. This pipeline visualizes a block cipher. The system takes a continuous stream of data and chops it into rigid, fixed-sized chunks. It processes each chunk individually and outputs an equal-sized block of ciphertext. Block ciphers require strict engineering trade-offs. Processing larger block sizes increases the mathematical security of the cipher, but it directly decreases the speed of both encryption and decryption. Here, a separate pipeline illustrates a stream cipher. Instead of batching data into blocks, this system processes the input continuously, 1 bit or byte at a time, merging the data with a parallel key stream through an XOR gate. A stream cipher relies entirely on a pseudo-random byte generator. This is an algorithm that uses the secret key to produce a continuous, unpredictable stream of bits, ensuring the resulting key stream has no repeating patterns for an attacker to exploit. Selecting between a block and stream cipher determines the structural latency and pipeline architecture of the entire software system. Secure software is deployed across physical infrastructure. We have to look at the macro network layer, where data packets actually travel. This map shows a frame relay network utilizing link encryption. In this setup, every vulnerable communications link is equipped with an encryption device at both ends. As a packet moves between nodes, the entire transmission is scrambled. The structural flaw in link encryption occurs inside the switch nodes. The packet must be decrypted back into cleartext so the hardware can read the routing header and send it to the next destination. The alternative is end-to-end encryption. The payload is encrypted at the source host and remains scrambled ciphertext for the entire journey, passing straight through the switches until it reaches the destination host. Because the network still needs to route the packet, the header cannot be encrypted. It remains entirely exposed as cleartext, while the payload stays scrambled. Leaving headers exposed allows adversaries to perform traffic analysis. This is an attack where an observer deduces sensitive information by studying the frequency, length, and destination of messages without ever reading the payload itself. Algorithmic perfection fails if the network topology is deployed incorrectly. Maximum security requires layering both link and end-to-end methods to protect the payload and obscure the routing data. The entire symmetric encryption model rests on a single fragile assumption. The system only works if the sender and the receiver already possess the exact same secret key. If a sender and receiver are separated by a hostile, globally monitored network, how do they establish that shared secret in the first place? Sending the key across the network exposes it to the exact interception the algorithm was designed to prevent. If the key is captured, the encryption is useless. Resolving this paradox required a new mathematical model, developed at research institutions like MIT, shown here at the William Barton Rogers Founder Building. In 1977, researchers here published the RSA algorithm, inventing public key cryptography. Symmetric algorithms provide the high-speed computational engine necessary for data confidentiality, but the engine is parallelized without a secondary architecture, public key cryptography, to securely deliver the keys.